In this video, we'll discuss the representational power of MLPs. In particular, we'll see that there is a huge difference in representational power when you go from 0 hidden layers to 1 hidden layer. And we'll also see that greater depth can make a network exponentially more expressive with the same width. Let's dive right in. Representational power of MLPs. So in the video on the history of deep learning, we already alluded to the fact that perceptrons can only model linearly separable functions. This is because their decision boundary is a linear function, just like in logistic regression. And this leads to the fact that they cannot learn something like this XOR function here, which is not linearly separable. So you simply can't come up with a linear decision boundary that doesn't make any errors classifying these two classes. In contrast, if you add a single hidden layer, the theoretical representation capacity goes from only linear functions for a perceptron to any type of function for an MLP. In fact, the universal function approximation theorem by Sebenko from 1989 states that any Boolean function can be realized by an MLP with a single hidden layer. And also, any bounded continuous function can be approximated with arbitrary precision by an MLP with a single hidden layer. So this is very powerful. And I have a couple of notes on this here. The first one is the main idea of the proof. So basically, you can show that sums of arbitrarily many sigmoids can actually approximate any function. In general, any type of squashing nonlinearity will suffice for this proof. And the technique of the proof is actually somewhat similar to the Taylor expansion. Now, this might already make you somewhat suspicious about the claim that if you need to actually come up with all these different sigmoids that you add together in order to get a function, you might actually have to add up a lot of them in order to approximate a function to a reasonable degree. And that indeed is one of the potential downsides of the theorem, which is that it doesn't say how many units you actually need in this hidden layer. In fact, well, for any given precision that you want to achieve, you can find a number that is finite, that is sufficient for the precision. But in general, if you want to have a single neural network with one hidden layer that ought to be able to represent anything, then it would have to have an infinite number of units. And the third note I want to make is that the theorem actually does not show that we can learn any function. It only shows that a multi-layer perceptron exists that has a single layer that approximates a function. And it does not show that this MLP can actually be learned from data, that we have an optimizer that learns it, that we don't overfit, and so on. So it's purely a result on the representational capacity of the MLP. But having said that, it's still an extremely important result, and it gives some theoretical backing to the idea of actually using deep learning for all kinds of different problems out there. Now let's think a little bit about the power of depth. So if you have a single hidden layer, all the computation actually has to happen in parallel. We can't reuse any information from previous computations. So if you have a function, for example, like this one down here, you would actually like to reuse information and basically learn something like in the first layer, you learn that there is this regular pattern, and in then the second layer, say where in this phase you're currently in for your current input, something like that. And if you have compositional structure, if you have depth, then you can learn something like this. And in fact, you can reuse pieces of computation that you do early on in the network exponentially often in terms of the network depth. So you can think about this as follows. If you have n layers with 2 neurons each, then the number of connections through this network is actually O of 2 to the n, and that's why you can reuse your initial computations exponentially often in the number of layers, because there's an exponential number of paths through this network. And in fact, there is a theorem that states that depth increases the representational capacity exponentially, whereas width doesn't. And the theorem reads as follows. A neural network with n sub 0 inputs and L layers of n units each with ReLU activations can represent functions that have this many linear regions. And so the important thing to note here is that this depth L is in the exponent, whereas the width n is only down here in the base. And so you can, with a neural network, represent functions like this one that have a lot of different linear, in this case, constant regions, and you could have an exponential number of regions in the depth, and you could still represent that with your network. So that's pretty powerful, and that's why that's one of the reasons that deep learning is actually more powerful than shallow learning. All right, this brings us to the end of this video. And as always, I'd like to leave you with some questions to think about for yourself. So this is the last video for this week, and I'm looking forward to seeing you again next week. Thank you.